Okay, well, let's get started. So, hello, I'm Aashish Chaudhary. I'm the Assistant Director of Business Development at Kitware. Along with me, I have David Manthey, the Technical Leader at Kitware. We would like to welcome you to our webinar on HistomicsTK. Next slide, please. First, I will give you a quick introduction to Kitware. Then we'll describe our HistomicsTK platform, including its architecture and core capabilities, describing the various ways it can be deployed and used to organize new and existing data. Then David Manthey will cover some example use cases and show us a demonstration of HistomicsTK in action. We'll wrap up with a slide covering some helpful information as you take your next step in working with HistomicsTK. If at any point during our presentation you have a question, feel free to type in the questions window for this live stream. We'll take a break for questions before and after the demo. Next slide, please. So Kitware was founded in 1998, and currently we have about 220 employees across the US and Europe. We primarily perform software and AI research and development services for our customers in government, industry, and academia. More people know about our popular open source platforms like CMake, VTK, ITK, and ParaView than they do about Kitware. We are proud of our long history of accomplishments in open source and open science, as it lines up well with our vision of making the world a safer, healthier, and better informed place. And since 2020, we are 100% employee owned. Next slide, please. We are a highly collaborative company with research efforts primarily funded by the US federal government, involving commercial and academia as well. We provide custom development, support, and training on open source platforms. Our expertise spans healthcare and life sciences, including digital pathology, surgical planning, medical imaging, and bioinformatics, plus energy, manufacturing, and defense applications focused on simulation, HPC, and data analysis. Deep learning is central to our work with a strong emphasis on ethical and explainable AI. Next slide, please. Most people know Kitware through the open source platforms we create and maintain. We are strongly committed to open source and open science, building vibrant communities, publishing results, and encouraging collaboration. You can find all our open source technologies at kitware.com. Today's webinar focuses on digital pathology. Please, again, reminder, type any questions you have into the window during this live stream. Next slide, please. So let's talk about HistomicsTK. HistomicsTK is our open source web-based end-to-end platform for visualization, annotation, organization, and analysis of whole slide images designed to scale from individual users to enterprise deployments. Like most Kitware projects, Kitware HistomicsTK started as open source collaboration, particularly with Emory University over the past decade. From the beginning, it has combined data management with human and machine annotation capabilities. Our vision is to unite pathologists and researchers, enabling novel algorithms and diagnostics in an accessible, scalable manner. The platform is customizable and integrates well with other tools and frameworks. Next slide, please. At the core of HistomicsTK is our data management model. We start with extensible authentication, passwords, OAuth, and more. Then we store data securely in asset stores, whether that's local file systems, network storage, S3 compatible buckets, or even data housed at other institutions. A key feature is that we handle data in whatever format it already exists in. You can re-encode mass images in a standard format if needed, but it's not required for basic usage. Once your data is imported or uploaded, you can organize it in countless ways. And here's the important part. None of these require copying those large underlying files. Everything remains searchable and customizable views, and you can extend functionality with custom plugins. Next slide, please. The first step in any project is to look at your data, then analyze it. We use containerized plugins that conform to the Kitware slicer 3D execution model. A user interface is automatically produced for each plugin based on its metadata. These plugins can operate on simple file inputs or integrate directly into HistomicsTK to manipulate annotations and meta information. While we default to Docker, we support Podman, a printer for your organization security requirements. When you're experimenting, it's useful to run algorithms on individual slides or just region of interest. Once you are ready, you can scale up to batches of images. Algorithms can run locally on a laptop or on remote workers that scale as needed. So I will stop here, and I would like to invite David Manthey to talk more about HistomicsTK and its architecture.
Thank you. So I'm the lead engineer on the HistomicsTK project, and the architecture from the beginning has been intended to be modular and extensible. I've got a image here showing a default deployment using Docker, where you have a host computer that has a small constellation of Docker images running, so that you have a server, a database, and then ways to communicate with workers. And the worker could be on your same computer, could be anywhere else in the world. And that worker can then run these algorithms. And so there's some basic use that is intended where you're actually just looking at your data and maybe making human annotations. And then there's the full way to have machine generated work run on that. And everything is API driven. So the architecture is intended to be extensible. And so when I do the live demo, if you see a web interface can do it, it can be scripted. And one of the virtues of having a web interface is that this works where you can have the server be anywhere and people have browsers on their computers and can access it, assuming that they've got appropriate authentication. And everything has plugins and entry points. So, the authentication, whether it's passwords or auth or LDAP or something else that we don't currently have implemented, can be just added as another plugin. And data sources, what image formats we read and things like that, again, are a list of ways that are extensible. And similarly, how we do data processing, what image algorithms are available is all extensible. And so the entire goal is to have this be a pluggable connection so that you can expand it to whatever you need to do it. And as Aashish said, we try to read whole slide images in their existing formats. I'll cover more of that as we go on. And so one of the ways we need to do this is it has to run somewhere. So this can be deployed in your institution or on your laptop. So if you're just trying this out the first time, you can do this on a relatively low-powered laptop. That works for one person or three people, but it doesn't work for lots of people. So you then might deploy it on a bigger machine. And that's just using Docker Compose, which is a fairly standard tool. And then it doesn't have to do that. We have example Terraform scripts for cloud deployments. We could also use Docker in the cloud deployments. And then recently we've had several people install this on HPC systems, and there where Docker is frequently not allowed, we often have converted some of our process containers to using the Aptainer format. And this is just an open container format that has much more stringent security than Docker does. And the worker nodes don't have to be the same as the main server. So your main server could be a simple EC2 instance that doesn't have a lot of power because it doesn't need that much. And then your workers might have a hefty GPU behind them because you're running algorithms where that's useful. And when I'll mention that we use things on like an S3 asset store, but that's it doesn't matter which cloud provider. We can work with all of them. So the heart of this is data organization. We import a lot of data from wherever you have it. And so if you have a typical research project, you might be starting with just a few samples where you have a few images, but you might also have things like the, an existing research project where you have 1,000 images or 10,000 images or more. And all of that's no problem. I've got a screen showing the Cancer Genome Archive project where it's got about 30,000 images. And these are just have been imported with metadata, and so this is customizable. So by default, it doesn't know what metadata you might have for your project. Each folder or collection could have its own metadata. So a research project involving kidneys, you might care about very different things than a research project involving brains. And that's totally understandable. You're going to configure this as needed. And Well, the focus of the Histomics platform is whole slide images and digital pathology. We do handle radiology files too with plugins that Kitware makes, so you can use VoluView to visualize those. And in my back image, I'm showing some radiology data that's been organized by DICOM series ID and studies ID. And you don't want to see every individual image of a CT scan, so it's showing a representative image and then like getting you a link there. And so this is all designed to be granular as needed for your project. You can group it as appropriate for your particular research task. It's not a one size fits all. It's very much we can tailor this to how you need to view it. All of this is publicly published, so you can figure this out on your own. But if you don't want to spend your time doing that, then that's where we can come in. Formats. We would love for the whole slide images to be in something more standardized, but that's not the way the world is. And so literally there are hundreds of variations of formats. There are some basic formats like DICOM and TIFF. There are some things that look like they might not be those, but are like, Apereo SBS or just a type of TIFF. And OME TIFF is yet another variant. And, TIFF is a whole wide structure, but there's all these other things, Zeiss files and Nikon files and files that come from other sources. And the goal is to be able to read these as they stand. We have tested this with a huge number of different formats, but there's always more formats. Someone's going to come up with a variation we haven't seen before, and we can just work with that. It doesn't take a lot of effort to add support for additional sources. And similarly, and so on my right, I have a list from some of the documentation of all the different file extensions that we have tested things and said, yes, it can read that file extension. And we use a variety of different libraries to accomplish this. So that we are leveraging other open source tools to make it so that we can read these things. So OpenSlide reads certain things very well, but not everything. And Bioformats reads other things very well, but not everything. And similarly, for efficiency, you might want to use read TIFFs directly with libTIFF. So all of that is transparent to the most users. They just know that they upload a file, they can use it. And similarly, annotations come in a huge variety of formats. And so some of these are common shapes, polygons and lines to represent things, but there's also annotations that are more complex, heat maps and grids and overlay images and pixel maps. And we try to support every type of annotation anyone cares about, and if we haven't covered everything, then it wouldn't be that hard to add more. And we have a native format for annotations, but we also read standard GeoJSON. We've had community contributions for plugins to read Apereo XML, and there's other formats that, DICOM annotation formats that can be handled. And so, the point of this is that your data can come in as it stands and doesn't have to be converted to something else. And so, here we have a poll question where I'm going to just ask, what whole slide image formats do you need to work with, and what do and what are you seeing there? So can we launch that poll so you can see some options there?
I'm not seeing the results now because the poll has ended, but I saw that the mostly TIFF for the SVS was the top choice.
Yeah. I suppose that's not surprising. Apereo has sort of was the first to market with the to have FDA approval for doing this. So they've sort of the de facto winner at the moment. So besides whole slide images that are single images, we also can handle things like later fluorescence microscopy and things with multiple channels. So you have a bright field image where you've stained it with hematoxylin and eosin, and that's very common. But there's also things where you've taken your image and you've stained it with different materials and fluoresced it, and so you can see the DAPI channel or the CY3 channel, or you're looking at some of the differentiations that you see where like the T cells are and things like that. And our software totally handles this, can handle any number of channels and any number of frames, can dynamically composite them so you can see them as you desire. And we can also handle things like Z-stacks and time series, and again, see these dynamically in various interfaces and handle different bit depths, so 8-bit data and 16-bit data and floating point data, And I have an image on here on the right, which is a relatively small scan from a Nikon microscope, where we actually have different XY positions. The microscope moves different areas, and then a little Z stack was sampled, and again on 5 different channels. And you can composite that together and can show off how that can be done. And we can do this with arbitrary axes. So if your software, you run a data analysis and you say, let me try varying this parameter and see what sort of results I get, you can do that parameter sweep and output the results into a file and then look at it very conveniently to scrub through that, like we were seeing, what's the actual best values to use positive pixel count for detecting, neurofibrillary tangles in brain tissues or something. And you can do that very efficiently with this, rather than trying to look at each individual image by yourself. You can, it's much easier to have a scrubber. Everything's customizable. So we can customize user interfaces. I'll go through some examples of this. You can customize this either like a dialog that just pops up some additional data, or it can be a complete application, which is totally different format using the same API under the hood. We can have additional data views. So, you can embed this in the data browsing pages, or you can have this in the Histomics UI as a panel of additional data. We can customize the file formats, as I mentioned, image formats, but also we've done things where we've integrated where, hey, I've got an Excel spreadsheet with some data. I'd like to view that in line immediately adjacent to my image. And the deployments, I mentioned that we can deploy this using Docker or in certain HPC systems. All of this can be tailored as your organization needs. For example, we had one organization who wanted to make sure that they ran a malware detector on anything that was uploaded. So, they have a malware plugin that will do that, and they want to go through a bunch of other certifications to make sure that they were conformant to their industries, their particular organization's security practices. And so all of that can be handled as needed. And so I'm going to show a few examples just from the slides, and then we can see them in live if we get to that. But the one example we have, a custom interface, is a guided labeling project. This is a project we've done with Northwestern. It's still ongoing. But the goal here is to allow pathologists to efficiently label images. So we divided the image into superpixels, just large regions that are try to have some of these regional boundaries land on image features. For training this and letting our engineers work on it who are not biologists, so we said, let me just take some simple examples where I was differentiating between tissue and the markers where a doctor has written on, a pathologist has written something on the slide, or the background. But in reality, this is being done by a placental pathologist who has 12 or more types of villi that he's distinguishing and wants to do that. So part of this was determine pathologists' time is expensive. They are experts and have lots of things they need to do, and you never have enough pathologists for your task. So how can you get them to label things so you can produce a decent model of your problem set and not waste their time? And so the idea here is that you'd have a algorithm to choose optimal labeling strategy. And this is, you can think of this as like you know what category A is, you know what category B is, and you want to know, what's the most confusing thing. And so, if you're categorizing, fruit or something, you go, this is an apricot, that's a peach, and something's, you're not certain. You want to have someone determine what the uncertain thing is, so you can learn it better. And so the idea here is that there's different certainty strategies. You can say, I would like to show the pathologist the thing I'm least certain, the model is least certain about, so they can say, this is this type of villi, or in our simple case, this is tissue versus a marker that someone's written on. And then from that, we can say, okay, I've had you train, label the 10 hardest things or the 100 hardest things. Now I can retrain my model and hopefully done better at that. And now the next hardest things are hopefully not as hard, but each step can improve your model. And the idea here is to have a user interface that's customized to make it as fast as possible for the pathologist to label his data, so that when they produce a model that does this, they can have a good model without having spent a lot of time doing that labeling. And then the page I'm showing here is a review. So you can say this is what was done, and what we're looking at is, what category was this binned into, and so if you had a junior pathologist do this, you could have a senior pathologist review it. And so this is, again, based on our same API, but a very different front surface. And then some tasks just require traditional image processing. You're trying to find nuclei as a step before you do another process. You can do this with traditional image detection techniques where you can say, I want to do color deconvolution to find like the hemotoxylin channel. I mean, it's one of the reasons we stain with hemotoxylin is to actually see the variation within the tissue that makes it more obvious to stand out things like nuclei. And then you can say, okay, I'm going to find this using blobs and say, okay, all these little blobs are my nuclei. And anyone who knows biology can see that there's a few that's been missed. And you can also see there's some areas that probably are like some sort of blood vessels or something that probably aren't nuclei that are here. So this shows both the power and limitations of traditional image processing. We have a standard library that can be built on to, it's open source, can be built on with these standard tools to build into more complex algorithms, or some of them might just be useful as they are. And so the entire idea here is that you don't have to throw machine learning at everything. You can sometimes just use standard image processing, and that works. And what this is there's a plugin that you can add, upload to the system and say, hey, I'd like to expose the detect nuclei algorithm, and I'm going to pick this slide and set a few parameters based on if you had particularly small or particularly large nuclei, maybe you have to adjust something, but it's intended to work at a certain scale. The other thing, and I'll show an actual live demo of this, recently there's been a lot of growth in an area called foundational models. So this is our latest machine learning techniques where you have a process where you show it a large number of labeled images, and you can say, hey, I now have learned this, but hopefully I've learned things that I didn't know I was teaching it. And the goal here is to have a basis for which you can build custom models on, or maybe the foundational model is enough to answer your questions directly. So as a demonstration of how easily it is to swap in and out different foundational models, if you go to Hugging Face, there's going to be a whole pile of these. So some of them are generic, you have Dino v2 and some of the UNet variations where these are just generic. How can I distinguish different things in images? And then you have custom pathology models, GigaPath, which is an Apache licensed. You have a Uni, which has a no commercial license unless you get permission from them. And then there's ones like Midnight where they're saying like, oh, let me see if I can train a model with less data and still get good results. And so these foundational models exist. And so if you're starting your analysis of a task, is there already a model that gets you most of the way there? Then you could use it. But if there isn't, then maybe you need to do something else. And so rather than train from scratch, you can try out these models. And so as a demonstration, we made a small plugin that implemented several of these models, just downloads them from Hugging Face, assuming you have the right credentials and permissions. And then you click on run a pre-analysis where we basically compute embeddings from an image, and then you can say, hey, how well does this space match? So in this instance, and again, I'll show a live demo of this, we said, find me the glomeruli in this kidney tissue, and hey, it found glomeruli. And there's a bunch of subtleties that I'll go into when I show that off. And so what foundational models are you currently using is our next question. So if you can launch the poll.
Currently we have 1 and 1 each for licensed and open source one.
Okay. Okay. So this is where some of those models, as people try these out, we'll see more uptake of that because that's definitely the latest hot thing. And so another case we have is we have a project which is with a BAMF aid where we're looking at kidney research, where we're trying to standardize how kidney grading is done. And this is where there are pathologists manually assess kidneys for instance, transplant viability, and what exactly constitutes IFTA, intertubular fibrosis, is something that people don't completely agree on. Even the top pathologists are not always convinced one thing is IFTA and one thing isn't, or how much lumina is showing, what exactly you constitute a tubule and where its lumina is. And so part of this idea was that you could use AI segmentation, and then produce some sort of standards that you could get the experts to agree on. And then if the experts could agree on, then maybe you could have a trained system to do this. So there's a project where we're working on this. We're using some community generated tooling, some work that's been done at University of Florida, and then trying to combine some of this with getting some of the leading experts from other places to basically agree on how these things should be scored so that you can have a more standardized method of doing this. And so this is just showing off one way that we can integrate existing algorithms into our system. And then we'll have one more poll question before I get to the live demo. But this is the, what challenges are you facing when you integrating AI digital pathology workflows? Where are your pain points?
It looks like the lack of training data and the deployment seems to be the topmost
Yep. Okay.
answers.
That's again, that's one of the things the guided labeling was to address lack of training data and deploying. That one of the goals of Histomics is to be able to deploy this so we can actually use it where the pathologist does not have to be adjacent to the actual computer or the data itself. So I'll just mention a few other tools that could work within our ecosystem. We have a project that's called ImageDefy, which is for image data identification and anonymization. So if you're going to publish your data in a peer-reviewed journal, one of the things you really want to do is be able to provide some of your data so that people can reproduce your results. And one of the things that's difficult is the data could have, your whole slide images could have metadata anywhere. And there's more information, we'll share these slides and you'll have that link, but basically there's interesting things where you can have a TIFF file where certain tools will, seemingly hide that it has certain PHI, but don't actually fully remove it. And if you could guarantee that you've removed the PHI before you share it, because you don't want to accidentally leak anything with PHI. There was an interesting case where the Cancer Genome Archive project, some of the labels, images in that project actually had PHI. They did not fully redact names and things off some of the labels, and they had to take it down for a while until they had addressed that. And you don't want that to happen to your data. So we have tools to help you with that. And this works on TIFF and DICOM files and can be customized to your workflow. And you might need to keep some data because it's clinically important, but you might need to scrub it from other data. And then I'll show off how we integrate with various algorithms, but one of the things we can do is we can use MONAI label as this is a server that basically is running machine learning workflows, and you can say, hey, I'd like to use it to do something. So you could use like segment anything or other models to do nuclear detection or some other project. And there's a whole model zoo that exists, and these can all be put into MONAI label, and then that can be accessed from HistomicsTK. And again, one of the virtues of open source is this was an open source collaboration from different people from different organizations, and added capabilities to our system based on that. So, and so now it's going to be time to do a live demo. So before I get there, do we have any questions in the question box?
David, I'm not seeing any questions in the question box, but I'm wondering if anyone wants to.
Feel free to ask.
Yeah. I know that we have covered a lot, so maybe it will take some time, but feel free to write any questions to say right now.
No, we do have, I see some questions, Aashish. Yes, so the source code is all available. This is open source, and we will share the slides at the end of this. And there be links within the slides to the source code. At the very last slide we'll have more links to some of this. And for the specific demo I'll show with like foundational models, we'll definitely include that as one of the links. And yes, we do have a recording that will be available when we're all done. And so basically, with the basic installation, you have a page that has some landing page that's going to be fully customized to your group. And then within that, we upload data. And to show off some of this that I mentioned before, I can have a variety of collections of different things I'm looking at. Actually, we'll go to TCGA. And so this is from the Cancer Genome Atlas program. And literally, here I've got 30,000 images in this directory. And this is an example where I've got, there's thumbnails here of my slides, and each of these has a name that's whatever name TCGA gave it. And then we have things like, what tissue types, and not all of this is populated for every item. And you'll see this columns labeled label and macro, and we'll do a search where we see that. And there's a lot of data here. And so you don't want to see all that data. So supposing we're just interested in kidneys. So I might type renal. And the first thing you'll notice, aside from the fact that some of these do now have label and macro images, and that's just whether the original data has it or not, is that the first thing that came up was adrenal, because renal is a substring of adrenal. And I didn't want that, so I could do minus adrenal. And hey, now I've seen kidney data. So, and you could also do more specific searches. You could say, oh, I only want FFPE preservation techniques, and from specific years, you can make this as precise as you want. And if you actually had a collection that you're happy with, you could say, this is the data I want to work on. I could select to copy it and then copy it, and this would just copy my list of images that I've got here. I might copy that to a folder specifically for a project. It doesn't actually duplicate the image data. It's just making references so you know what's in there. And so that's often a typical way to start a project, is you take your existing data and say, let me see what I have. Do I need more data? Do I have enough to answer these questions? Let me do my exploration of the data I even own so I can actually do the process I'm working on. In this instance, this data happens to have been downloaded and stuck on a spinning disk that's right next to me here. But it could equally well have been pulled from an S3 bucket, or located on another institution where we had federated the data collections and viewed it from there. There's a variety of options for this. It doesn't have to be local to my computer. It can be anywhere. I don't necessarily want to download 18 terabytes of data to do something. I want to just be able to use it where it's at. And so when we have specific data, so I took one of these kidney samples that was in this list, and I said, oh, that makes a good example for this. So I have made a collection just to show off this, and I'm going to show, I'm browsing in, and this has got a standard folder structure that we look at. And here I've copied one of the TCGA images, and I'm looking at this, and I'm just going to drill in. It's got some other data. We won't worry about that right now. But if I open up this image, I can see that having gone into an image, I can see the whole slide image. And this is interactable, so I can see what it is. And this is my data viewer. And I can see it's got some annotations. We'll get to that in a bit. But it's got metadata. This all came from TCGA. So when I downloaded this into TCGA, I said also process the metadata and make sure it gets tagged in our system, so that way I can do search on these things, and I can look at them, and you can read whatever metadata is there, and it will tell you, this is like when various things were done to this patient, and this is what's known about it. And there's some things that are listed as unknown that we can guess at, but this is what the actual data that's there. And there's further information that you can expose to admin users that you can see. So for instance, this has got a resolution that is considered 20x. So this is the magnification that is used. And colloquially, that's like a half micron per pixel. This is not quite, it's very slightly more than a half micron per pixel, but this is the sort of thing you can learn about your data and look at how this is done. And there's further internal metadata that we can look at that's more complicated, and depends on file format. But the thing that we really want to do here is we want to actually start working on it to do some analysis. So I'm going to open it in Histomics UI, and this is our default viewer for doing annotations and running algorithms. And again, this is just but it's itself done as a plugin to the system. So even though this is our primary user interface for histology, it is itself just a plugin, and so any other plugin could do something similar. So one of the things I can do is, for those of you who are not kidney experts, very quickly, we have something called the glomerulus, which is this round item. It has biological meaning. I'm not going to go into that. I'm not a biologist, but you can also see that like this is part of a glomerulus. So they're round structures, vaguely spherical, and depending on where the slice of tissue is, you can see different portions of that sphere. And so one of the things we can do is we could create a annotation. So I could say, hey, I'd like to find my glomerulus, and you'll see how badly I can draw. Well, and then go, oh, I didn't draw that very well. I could edit this and adjust it, but I'm not going to do that right now. And so here I've got an item that I've drawn on, and I can select it and say, oh, this happens to have a area, and it's given to me in both pixels and microns, and it's also giving me the perimeter length of this, which is also given to me in microns. And the important thing is here is scale. So in a minute, I will show off using a foundational model in this, but the foundational model has to be tuned to the scale of thing you're finding. So it's important to know here in this glomerulus, it's roughly 200 microns across. That's sort of the important aspect of this. And so we'll hide this item for now because we want to show something else. And we have a tab here called analyses. And analyses are any of these additional processing plugins that get added to our system. And you might have just one or two, or we've seen customers who have literally hundreds of them as they develop things. And they might be different versions. They might be different projects to try things out. So we have some standard ones like the HistomicsTK library that has things like nuclei detection. We have things like the MONAI label plugin that runs MONAI label attachments. And the one I'm going to show off is one we developed just to show off foundational models. And this is the HistomicsTK similarity project. And it's just got a single option here, which is embedding similarity. You'll notice there's just one, and that has produced some data here on my left. Now, again, if I had gone to one of these, some of these toolkits have lots of sub-algorithms, and others of them, like the one I just picked, just has one. This UI is generated from the Slicer CLI execution model metadata. So this is a way to package up workflows to say, what are my inputs and what are my outputs? This is critical in any data processing where you can say, I would like to know that it takes an input image and it outputs an embedding file, or it takes a annotation and outputs another annotation. So this key point is a set of coordinates, X and Y. This is something that every workflow that's going to use these has to have this rich metadata. And so if you're familiar with command line tools, it gives you a little bit of metadata. We need more to actually do these things well and hook them up. And so this is the process that we have. And so what this process has done is we've used a foundational model to run compute the embedding of each little tile of the image. So the way these models work is they frequently work on a 224 by 224 pixel tile. I'm going to show off GigaPath, where this was trained at 20x, and the 20x, 224 pixels across means half micron per pixel, 112 microns across. And so for each little 112 by 112 micron region, we've computed an embedding, and it has some options that show like a stride. So we actually have overlapped these, and we've done that computation. I did this ahead of time because it takes like 5 minutes on this image on my GPU. And a bigger image would take longer, and no one wants to wait 5 minutes. So you can pre-run this, and we can run this on a single image, or we can click this multiple and run a whole batch. So I can say, I want to run this on the entire TCGA, and depending on how good your GPU is and how many of them you have, this is something that'll take a short time or weeks. So I pre-computed these embeddings, and I saved them so I can give a demo. And I am just going to choose the one I did for GigaPath. And so what this does is it knows that I have this file. In this case, it's, for those who know the image processing, it's stored as a standard NumPy file of this matrix of data. And I am going to pick a point, and I want to find glomeruli. So I'm just going to pick this glomerulus. I'm just going to click the center. And in a moment, This has actively, by me clicking on that, compared region patches with a cosine similarity transform to actually produce the which areas have the best response. There's a bunch of data here to adjust this. So anything that has a response, a cosine similarity lower than 0.75 is just not shown. And so it's scaling 0.75 is transparent to, in this case, I chose yellow. And you can see, hey, I've got a decent response from this. And not only did it find my glomeruli, but even some of these glomeruli that have been sort of cut off, it has found. So like here, this is a bit of a top or bottom of a glomerulus, and it's seeing a bit of response there. It's not as confident in that. And part of this is I asked for a specific scale. So I said, I want to aggregate 3x3 regions at a stride of 112 pixels. So that means that I'm actually looking at a region that is 224 is the patch size plus my stride. So it ends up being that I'm looking for things that are 224 microns across. And so my glomerulus was 200 microns across, and this matches. And so if I click on a different area, we'll make another color to show things off. So I'm going to say, let me show something in red, and I'm going to click another point. And I'm going to say, hey, maybe I could find this tubule here. And if I click on this, it decides that a lot of things look like those tubules. And then there's some areas that aren't. And then glomeruli are distinct, so it said those aren't glomeruli, those are whatever that region is. And now you get to the point where it's clear that I'm not actually a kidney biologist, because I can't tell you whether that makes sense or not, other than that it looks like something occurred there, and then why are these regions not showing up? And the thing is that the tubules are actually much smaller than my patch size, so there's a good chance that I can't get that distinction with this model at that. I need a model that's trained at smaller items, or I need to try to see if it could just be run on a higher resolution and see if that actually will help me with the distinction. And sort of one of the things to go back to this is I might want to say, how well does this compare to a different foundational model? So we'll leave our glomeruli up here, and we'll show off picking another foundational model. And so, still there, we pick a, so Dino is not a pathology foundational model. It is just a model that has been trained on images in general. And it's sometimes a base for these other models. And if I click on a glomerulus and give it a moment, it feels everything looks similar, except maybe that spot. I mean, it found tissue versus slide, but this is not a useful result. And so you can say, great, my pathology trained foundational model clearly has better distinction within pathology than my non-pathology foundational model. Now, there is some subtlety here that if I asked for a threshold that's much tighter, and I reprocess this and say, try it again, but now use that value, now it actually almost looks sensible. I mean, it missed some things and it found some things. And so, maybe the model's not terrible. Maybe it's just not very distinct in pathology. And so this is just a way that we can show off using our tools with other people's models to say, are these models promising for my research project? And I'm just going to pause there and see what questions we've accumulated and ask if anyone else has more questions.
Yeah, David, there are two. Actually, there's one relevant question. The question is that, do you provide docs examples of how the analysis tools package with HistomicsTK can be used standalone outside of HistomicsTK UI framework?
Definitely. So one of the entire virtues of this Lyser CLI execution model is that you basically have something that we can have any amount of integration you need. So it can be just a simple interface where if you could run this as a command line program, you can package it up so it can use it in this manner, but you can also use it outside of this. So in this case, I'm using Docker, but again, we could have used Aptainer or Podman or one of these others. And with that same package, I could have typed, hey, I'd like to run this on my command line. So like when I'm running the embedding to first do the calculation, I could run it through this interface, or I can type it on the command line and run it on the command line, or script it in any way I want. There's some tie-ins where we say, I'd like to contribute back an annotation here. So like the output from this is an annotation JSON file, and I could say from the command line, just give me a JSON file. Or I can say, oh, upload it to this interface so I see it right away. So it depends on how fully integrated it is. There's some of the things like the guided labeling, which we were showing earlier, where there Some of the models are very integrated in and would be complex to run outside of the UI, but could be done. And others are not as complex. So like the blob detection is something you definitely can run. It's even a Python package you can run separately. And yes, so that is the how can you run this outside of it. We have several points of documentation. Because of the way open standards work, this is sort of like a bit scattered. So we have one page of like trying to be the landing of here's everything you need to know to package one of these. And it can be very simple, like literally if you have a command line tool that you can run, it should be straightforward to package. There's a little bit of complexity to make sure you get the data types right. And then once you have it that way, it still can just be run as a command line tool or dropped into this. And then going back to multimodal models, yes, definitely. There's another project where we actually had a customer integrate this in where he was using Claude to ask questions and transmitting an image of what he was looking at and trying to answer, visual answers. I tried a terrible bag of words model where I said, can you describe what you see in each patch? So I pick an area and tell me about it. And that did not do nearly as well as I was hoping for. I was actually trying to do that as an example of this before I used the foundational models of say, can I get one of these models to explain what I'm looking at? Because I'm not a biologist and I say, what is this region? And sometimes it made sense, looking at a brain tissue and say, hey, this is brain tissue and it seems to have neurofibrillary tangles. You're like, great, this is working great. And then you click somewhere else and it tells you something that you're like, this is clearly not whatever, not liver. It's, I can tell the difference between brain and liver. And sometimes, you can see whether the modal models are working well or not. And there's different ways to tie that in. Like we could have passed in to our model the metadata we had. You could have passed in a path report that you had adjacent to this. What we pass into the model can be as rich as you want, and then what we get out can be any form of annotation. So here we're doing a heat map annotation, but we could have done perimeters, to find boundaries. We could have done write-up where it gives you a verbal description, a textual description of what you see. All of that's quite straightforward to do, and it's just a matter of where you want to see it. Like currently, there isn't a great way to look at the textual description here. I mean, I do see some data, like it could say, oh, these are the parameters that were used, and it tells me it found 160 areas, individual points. And to be clear, like this is, might be 4 or 5 points in it, but the number of points it found positive signal on was 160. That may or may not be useful information, but you can have your algorithm output things. So we could have a whole text block here or somewhere more convenient. This is just a default way to look at it, and so yes. So,
David, there's one more question. I don't think we got into it earlier. So the question was that, did we talk about conversion from vendor-specific format to DICOM?
Yeah. So basically, DICOM's a big standard. So there's image formats and there's annotation formats. And currently we have tools that aren't explicitly packaged here, but would be easy to do, where we've said, hey, when one of our other projects is like, here's a command line tool where you can basically say, convert this image, any of the images we can read to a DICOM whole slide image. And the DICOM annotation formats are actually something that we still need to have conversion tools to convert to and from DICOM annotation formats to this. We have some tools that do that in the radiology space. We are not fully, we need more work on that, but that is just work. There's nothing challenging. There's no technical barriers other than time and funding. It's not a insoluble problem. It is just a matter of dealing with these different formats, because again, for annotations, I've got points and polygons and heat maps and grid data types and XML markup and all sorts of other things you could add in, and you have to be able to say what is the way to correspond all of those together.
Yeah, one thing I would like to add is that DICOM definitely is very important for us. Not just for this particular effort, but for other efforts as well. So that's something we definitely keeping an eye on and working as we get funding, as David mentioned.
Yeah, and to the last question I see there, yes, there is definitely limitations to converting to DICOM. We have used other people's tools for the most part to do this, because again, we're trying to leverage what already exists. And part of that is like there is no, literally hundreds of formats. There's no consistency in how those formats have stored metadata. We've tried to standardize this in certain presentations. DICOM has very strict standards saying like this is like the tag for this field, and you'd be like, great, here's where patient age goes. Do I have patient age in any of this mess I got from file A versus file B? And that is still probably every format out there converting to DICOM, you'll get something. Well, you get everything you wanted, and that's a case by case basis of like, can you do the job correctly? And that's so that's a intimidating thing to work on, to do it, just because there is so much variation in the wild. Literally. We've seen cases where people have like OME-TIFF, which is a standard that someone's published, and people have miswritten OME-TIFF, so it's almost to the standard but not quite, and they've stuck their metadata in a non-standard spot. And so then you have to say, can we automatically do that? If it's in the standard spot, we're not bad at it. If you're in a non-standard spot, well, you have to just to customize that. So that's part of this where for your data science side of things, the data processing is not the work that needs to be done before we can do the real work. It is often the real work that needs to be done, and that's just part of how you get your data for your project. And so, anyway, this is just showing off a relatively straightforward example. The code on this is available on GitHub, and this one I tried to document fairly clearly to make it easy to follow, and feedback is most welcome when you get there. If we go back to our data viewer, you'll actually see, like if I navigate away here, you'll actually see like these were the files I was using. So I ran my pre-embedding code, and this produced a NumPy file, and that's actually one of the source inputs I was using. And now that I've just done a bunch of demonstrations, you'll see all these extra heat maps that I generated, and we can click on them and see them here too. So this is just another way to view data that you've got, and there's all of this is permission control rich. So you can say, hey, I would like this this annotation to be visible by by different people. So I've made some examples here so we can show this off, but you can say anyone's allowed to view this, or these people are allowed to edit it. So part of this is when you have a project that has multiple pathologists, you might want each pathologist to annotate something and then see if they're in agreement, or you might want them to collaborate, and those are very different use cases. And so if you want to see if they're in agreement, you don't want to sort of pollute the data, so you want each person to have their own copy and only see their data and not the other person's. If they're collaborating, you go, hey, let's, I'm going to mark this up, and then can you correct anything you see that's wrong? And then I can look at your history of how it changed and see whether I should have learned from this. And so the permissions controls intended to be as granular as needed, and can be quite complicated. And there's some things where we have social debates about, if I copy an image that is annotations I'm allowed to view, but you created, and I copy them to a directory that's you also have permissions to, who owns the annotations after they've been copied. And so then there's no technically right or wrong answer to that, so much as a social answer that you need for your project for that. So there's some complexity to that system. And so going to and then just to show off some of the multi-frame data. So this is an example I have permissions to show off. And this has got a set of 5 different channels. And so I can say, hey, only show me the CY3 channel. And you go, oh, that signal may not be as bright, so I can enhance it and see a histogram. And you can actually work with fairly complicated data here and use this for image exploration. This is quite fuzzy because that's a Z-stack, and I think over here might be more. Yeah, that's much more in focus, and I can see that there. And again, this is integrated, so if I open it up in this interface, I now get those same controls over here. And so I can say, hey, and if you always wanted to view a certain thing, you could do that. Um, and we'll again show the same thing, just in a different context. And you can, so these are tools that are flexible and can add. This whole panel did not exist in this image because this does not have multiple channels. So you don't get those controls because they aren't pertinent. And so that's just showing off some of the tooling we have and the capabilities. You can work on whatever research projects that you actually are developing and customize it to reviewing it. And many of the plugins are, some of them are unaware of multi-frame images. So the fact that this has a Z-stack, it might not know. So some plugins will just operate on the first Z-slice. Others are aware. So you can say, hey, I'd like to take this particular slice. We have the ability to pass in like what you picked here into an algorithm. So you can say, I have a DAPI channel, which ought to show nuclei. And so, this tells you scale right away if these are the nuclei, but I can say, hey, I'd like to pass this into my blob detector to find nuclei. The example that we have for nuclei detection, will actually take that and process it, knowing that it has, that this is the thing I'm looking at, not this, because this I'm not going to find the nuclei. so just demonstrating that we can hook all this through so you can actually see what's going on and how it relates. And so I'm going to go back to our slides and just say, okay, we'll have one more poll. And this is just asking what tools you are currently using to manage or analyze your digital pathology data.
Okay, so we have one on the commercial platforms, Philips Leica 3D stack. Let's see. We're still voting. So we have one for QPath, two for Path Presenter, one for in-house custom solutions, and two for commercial platforms.
Okay.
So
And
far.
then, great.
Let's see if it changes. So looks like Path Presenter is the common one along with the commercial platforms.
Great. Okay. And then just to end up, like, there, where can you find the source? There's a link here to some of the source that's distributed in a couple different Git repos, and we'll include more of that with the follow-up email. If you need help, we do have a, a discussion forum, and we also have a place where if you want to have us help you directly, Kitware does open source, but we are happy to partner with you and be specific. If you ask a question in GitHub, if it's fairly short, we'll happily provide an answer. But as it gets more complicated, we have to figure out how to work together and do that. And we are a very collaborative company. We love being subs on contracts. We love being co-PIs. We are happy to do this on commercial or federal opportunities. And if you want to customize the software to meet your custom workflow or to take your algorithm, you go, I've got an algorithm and I don't know quite how to do this, you can figure it out. We have documentation that should let you do that. But if you don't want to spend the time figuring it out, it can be much more effective use of your time to do what you're good at and let us do what we're good at than to have us do what have someone do something they're not an expert at. And so, just as like I want a pathologist to tell me what my kidney is, I also want a software person to work with your software. And so that's where we're. So here we are, and let us know how we can help, and we'll again send out the slides and follow up links at the end of this. And any final questions out there? Okay. Thank you so much for attending.
Yeah, Thank you all. Yeah, no questions. I'm not seeing any questions. I see some thanks notes from folks.
Okay.
And I see one response on the poll earlier was that Google Healthcare is another option that people use. Uh,
Great.
but yeah, thank you all. Thank you all for coming here. And if you have any questions afterwards, feel free to send an email to kitware@kitware.com or get in touch with one of us over LinkedIn or elsewhere.
Okay. Thank you much. Have a good day.
Yeah, bye all.
Bye.